the goal of these two seminars, so today and next week, is I want to introduce to the foundation seminar a method of actually getting a somewhat more concrete example of a non-standard model. I guess there's been several results already which kind of tell you, okay, like there's this model that you intended, but we can also do some like trick with the language to like force there to be more objects than you wanted in the model of your theory, or less objects, like with the downward and upward Lowenheim-Skolem theorems, or also the incompleteness theorem, sort of saying that uh, like that's another way of pointing to the existence of like these weird what are called non-standard models, but it doesn't actually sort of give you any sort of grasp as to what an example of a model could be, and like sort of what do the objects look like in it, and sort of why does this non-standardness occur. um, and so that's what I want to get to, um, and in order to sort of achieve more in these two lectures, today is basically going to be uh, doing doing the grunt work. um, and so it might feel a bit unmotivated. I'm going to be talking about filters and ultrafilters, and so for now, I'm kind of just hoping you'll uh, accept filters as a interesting gadget that is not necessarily like completely motivated thus far, but they'll be useful for next week. One sec, let me grab my pen. Okay, so first definition. What is a filter? So a filter, is sort of in structure. It's much like a topology on a set, but it has different axioms. And the idea is to, instead of classifying openness, it classifies largeness, and it's sort of a finer notion of like what which sets are considered large than like just talking about cardinalities of sets. And we'll return to that idea in a second. So yeah, filter is on a set X is a subset of is a set of subsets of X, which decides which subsets should be considered large. So let me write that.
Do you know who first defined filters?
No idea. I just came across them in the rising entropy article, which there was like a sort of blog series that is linked in the notes.
Okay.
So it's which subsets. And here's sort of the rules that it needs to satisfy. So first, the whole set is large. So you have to have the whole set itself in the filter. Secondly, the empty set is not large. So I guess these are the two like least controversial statements you could make about largeness. Maybe the first one is a little controversial if, like, I don't know, if X is just a very small finite set.
So does this implicitly require X to not be empty?
Yeah, because then the empty set can't both be in it and not in it.
Yeah, so a filter is a non-empty set X, blah, blah, blah.
Yeah, well, I don't have to. There's just.
Yeah, or you've left it implicitly there. That's fine. Got it.
Yeah, well, as long as you satisfy the first two axioms, like you're not gonna X can't be an empty set anyway. Okay, the third one is about supersets. So if you start with a large set and then you find some superset of that set B, then B is also large. Whoops, not subset. B is in F. So therefore, like also unions of large sets are also large because you're just creating a superset. So it's a and then finally, if you have two large sets, their intersection is also large. And so therefore any like finite intersection of large sets is also large. I'm going to give an example now, which we can play around with to sort of classify the filters on it, just to get sort of more familiar with filters. But this is going to be the filters on a finite set, which for the purposes of next lecture, kind of completely uninteresting. The more interesting case is when you have X being an infinite set. But let's just understand this first. So I'm going to draw a Hassett diagram, which is just a neat way to visualize what the poset of subsets of X looks like. So at the bottom, we've got the empty set. Then just above that, there's three singletons. And then above that, there's the pairs.
So, Billy, you've switched to 0, 1, 2 when you wrote X is 1, 2, 3. So
Oh yeah, I've done this many times.
before you write all of them, yeah.
I do actually use 0, 1, 2. Thanks. Now 1, 2. Okay, and I'm gonna just fill in the sort of edges that describe subset relationships when you read them upward. I've drawn this a bit compact, but I mean, if you've seen this before, that you already know that there's a badly drawn cube here when you look at the edges. But that can be useful for intuition later. So what are some example filters I can pull out of here? To be clear, I've drawn all of the subsets of X, and we're gonna pull it, like figure out which of these subsets can we collect into a filter that satisfies all the axioms. So a way to proceed in light of the third axiom is, okay, whenever you have a large set, all the supersets are also large. So you need to, like, you might as well just start from the top and sort of go down slowly and add sets as needed. So you can be very lazy and just have the whole set as large and everything else is small. And you can easily verify that satisfies all the axioms. There's no like other supersets, and there's no interesting intersections going on. So that's a filter. That's called the trivial filter. Then if we travel down, let's just add one more set to the filter and see if it's still a filter. And in fact, if we just add 0, 1, there's still no more interesting intersections. You still just get one of these two sets, and there's no more supersets. And so clearly, so that's also a filter, and there's two more that are like that if you pick the other two pairs. And now, if we try and introduce an interesting intersection, say if we try and put, let's put we've got 0, 1, 2 in there. Let's put 0, 1 and 0, 2. What happens by axiom 3, you have to also throw in the set with just, oh, whoops. Sorry, not that set. The set with just 0 in it, because that's the intersection of those two sets. And you'll find that this actually gives you the set of all subsets of X such that 0 is in the set. And we call these filters principal filters because they're characterized by, like, you just say all the subsets which contain this particular element in mind. And again, there's two more like that. There's two more principal filters, i.e., you have all the supersets of the set containing 1 and all the supersets of the set containing 2. Those are also two other filters. And is there any more? No, there's not, because if you, I mean, this isn't a complete proof, but just for example, if you start with one of the principal filters and you're interested in adding, I guess, any other sets in the diagram. So, for example, if you have the 1 point set containing 0, you can't add the 1 point set containing 1 because the intersection is empty. So that's actually all of the those are all the filters on this set. And so now let's talk about the filters on an infinite set. So I'll go over to the other board here.
I'm a bit surprised by the fourth axiom. Can you say something more about it? I just don't see why you would expect the intersection of two big sets to be big.
Yeah, so I'm pretty sure. So when we do the, I guess I'm sort of, in absence of anything else, I'm kind of just motivating it by this idea of largeness. And so I guess that's exactly what you're asking. How do you sort of extract this condition out of wanting to classify largeness? I don't know. There might be a way to do that. Like, I think you can sort of, there's probably some way to motivate the reason why you can't have infinite intersections, and so this is kind of just a choice to only allow finite intersections. I think is probably the more probably gets closer to answering that question, because you can have infinite unions because you can just have any supersets. But
yeah,
as far as
I think it's.
As far as I remember, the original example of a filter is just the set of all neighborhoods of a point in a topology. So then it's closed under intersections. So
I think I think a better answer would be something more like I haven't fully worked out the details of the proof from next week, but when we I'm hoping to just find the need for this axiom amongst the inductive proof on the complexity of a formula that involves conjunction, or maybe it's disjunction or something, will require the intersection to also be large.
So I can. Yeah, sure. Okay, thanks.
Okay, so let's talk about the case where x is the natural numbers, because that's the example we'll be interested in. So let me try and draw the analogous diagram for natural numbers. So we've got n at the top, empty set at the bottom. And just like before, above the empty set, we have all the singletons, 0, 1, 2, and so on. There's infinitely many of those. And above that, you also have the pairs and then the triples. As we go up, we're getting just all of the finite sets are being arranged here. So you could imagine them sitting in little levels of your poset. But they stop at some point, and you sort of enter the infinite set territory. And so I'm going to tell you about the co-finite filter here. And so the interesting observation here is that the finite sets are not half of this diagram. They're kind of they're obviously a very small part of the diagram because of, I don't know, cardinality reasons. But what we're actually going to do is reflect this part of the diagram to the co-finite sets up here, which kind of has the same shape. It's kind of the same data, but it's a co-finite set is just a complement of a finite set. So it has all of n except for finitely many points. So it looks roughly the same. Let me just label some things here. And so here you have things like just like you had the singletons, you also have the co-singletons up here. Like an example would be, say, n without 0. So there's all the co-finite sets, and between them here is this like large scary territory of infinite but not co-finite sets. I guess you could also call them infinite and co-infinite sets. So both the set and its complement are infinite sets. So some examples are set of even numbers, the odd numbers, I don't know, prime numbers. And this is the sort of part where the filter is free to sort of make decisions about, like, a filter could say that the set of all even numbers is large, but the set of all odd numbers is not large. I'll come back to this when I talk about ultrafilters, but I guess the example here is that the set, the following set is a filter. F equals the set of all subsets of n, or it could be subsets of any set x, really. But I'll just talk about n, such that x, well, not x, n minus that set is finite. So if you just decide to say only the co-finite sets are large, like you're being very strict about, like you're only like a large set if you have all, like if you contain all but finitely many points of the entire space, then that's what the co-finite filter says. Okay, I'll move on, but we'll come back to this slide again in the future. I guess I didn't sort of talk about just verify that the axioms are true of it. So clearly X is co-finite, the empty set is not co-finite. Supersets of co-finite sets are still co-finite, and intersections are as well. I guess I'm leaving you to verify that mentally on your own. But the co-finite filter is kind of is pretty like prototypical of the like kind of starting point of making an ultrafilter. It turns out that all the interesting ultrafilters contain the co-finite filter. And making an ultrafilter comes down to making choices about which sets in this sort of uncharted territory are also large. Okay, let's move on to the next section. Okay, so those three examples I gave across those two boards were trivial filter, where you just take only the whole set is large. Then you have the co-finite filter and all the principal filters. Okay, this is the next lemma I want to prove. And this is just saying that if you start with any set of subsets that has the finite intersection property, then there's a minimal filter containing it. So the finite intersection property is just saying any finite intersection of the sets in your given set is not empty. So it's essentially just saying that you're not going to violate the third axiom just by intersecting finitely many sets that you've started with. And we'll use this lemma at some point later. So any subset S with the FIP finite intersections are non-empty has a minimal filter containing it. And so I'll just give a sort of, we can just give an example, which is, I guess, in the example from earlier, we started with the set 0, 1 inside that 3-point set, and we also had the set 0, 2. And so say that this is our starting set S is the set containing these two sets. If we want to make a filter out of this, well, we need to satisfy the third, was it the third axiom? The fourth one, the intersection one. And so therefore we need to add in this set, this one here. And then we also need to satisfy the fourth one, which is we need all the supersets, which just is a matter of adding the whole set in this case. But that's the sort of two-step process to constructing the filter. Really is first you close downward under intersections. So take the closure of this set under intersections, and then close upward under supersets. I'm not going to give a super detailed verification of the axioms for this, but that's the idea.
So in a case when X is finite, this minimal filter has an easy description, right? It's the set of subsets containing the intersection of all the things inside S.
Yeah. And in the infinite case, like you're just describing it as the set of all supersets of finite intersections of
S. Exactly. Yeah, okay. Makes sense.
All right, any other questions for now? Okay, well now I'll define ultrafilters, and I'll come back to some of my examples from before and talk about ultrafilters on those sets. So a filter F is an ultrafilter if every set is either large or co-large. And so concretely, what I mean by that is the fifth axiom that you can add to the collection, which is for any subset A, you have A is in the filter, so it's large, or X minus A is in the filter. So another like definition of ultrafilter is that it's maximal, and I'll actually prove that equivalence or one direction of that equivalence later. But this version is just saying take any set you like. The ultrafilter is like maximally opinionated on it in that it either says it's large or it's so small that the complement of it is large. And so what you'll find is okay. Let's go back to some of the examples from before and talk about which are ultrafilters. So the ultrafilter condition, in a way, like especially for finite sets, means you have like half of the sets. So if you can kind of see the cube on here, maybe I'll sort of draw it again next to it. The cube here looks something like this. And here, actually, let me redraw that like that. Here, the principal filter containing that sort of starts with this set here, you can see it's sort of one face of the cube, and it's exactly half of the sets. So principal filters are ultrafilters, but they're kind of just the boring ones. So in the case of the infinite, starting with an infinite set, the principal filters are also ultrafilters here. But we'll find that like they're not super interesting for when you go to create ultra products. You kind of just end up with what you started with. And so the real interesting ultra filters are the ones that are on an infinite set, like the set of natural numbers, but which aren't principal. And what you'll find, which is what I'll prove now, is that not being principal actually forces you to remove all of the if you're an ultra filter, you can't have any finite sets. And so what that means is you contain the co-finite filter. So in this picture, it means if you want an interesting non-principal ultrafilter, you can't just stop here. Let me restate that. I guess let's look at what if you think about what a principal filter looks like on this sort of diagram here, it kind of just contains the half of the whole thing. Like it's sort of dense in this diagram, but you have like exactly half of everything at every level of this diagram. But when you have a non-principal one, it ends up looking a little more like this, where you sort of include all the co-finite sets. So that means you can't have any finite sets. And then you have to kind of just get half of this stuff here. And so that means picking between the even numbers and the odd numbers. And I think that's kind of where like the sort of large analogy kind of breaks down, because like who's to say that the even numbers are large in the set of natural numbers and the odd numbers are small. It's kind of I don't know, the analogy doesn't really track there, but But let's go ahead and prove what I was just saying, which is that if you want to be non-principal, so you've actually got an interesting ultrafilter, then you at least have the co-finite filter. So that's the next lemma. Sorry for going back and forth so much. Hope you can keep up. Thanks. So every non-principal ultrafilter contains the co-finite filter. Okay, let's prove that. Oh, and you'll observe that this actually means that you can't have non-principal ultrafilters on a finite set because the co-finite filter only has infinite sets in it. Okay, so consider so equivalently, this amounts to proving that F, the non-principal ultrafilter in question, has no finite sets. So consider some finite set A, subset of the whole space. And let me draw a picture here. So this is all of X. This is your finite subset A. And so there's finitely many points inside it. And the observation is that if I take the complement of, say, one of the points, what I mean is exactly this set here, where A is one of these points in the finite set A. And so what that looks like is this. So it's the whole space except for exactly that point. This exactly because the filter is non-principal and it's an ultrafilter. This set has to be in the filter because this singleton set is not in the filter. Because if they were, we need at least one of these in there, either this set or its complement, and this set isn't in there, so its complement has to be in there. But then note that if we take the intersection over all the elements in A of these large sets, we just end up with the complement of that whole finite set A. So that's a way of just taking any finite set and showing that it can't be in the filter, because then we're contradicting that this is in the filter. Any questions about that? Does that make sense?
Wait, sorry, so why can't you have A and X plus A in the filter?
Because then the intersection would also have to be in the filter, and the intersection.
Right, okay, of course. Yeah, okay.
Yeah,
Yep,
so
makes sense.
yeah, that I was going to say before that the condition 5 is written as a sort of inclusive OR, but by the intersection axiom, you can just read it as an exclusive OR.
Yeah, that makes sense. Okay, got it.
Okay, so if we want, so the lesson of this is saying that if we, well, I've told you that the only interesting ultrafilters are the non-principal ones, and so this is telling you that to make an interesting ultrafilter, you're going to want to start with the co-finite filter and then fill in the gaps of all the decide which infinite but not co-finite sets count as large. And so now I'm going to prove that there actually exists such non-principal ultrafilters on an infinite set. And we'll do that over here. Okay, so this is called the ultrafilter lemma. Which says that every filter is contained in an ultrafilter. And so, yeah, as I was saying, like, say we're starting with the co-finite filter and we want to find some ultrafilter that it's contained in. I was talking about that gap, that sort of infinite gap between the infinite sets, between the co-finite sets and the infinite sets. And there's uncountably many sets there. So I don't know, what's everyone's favorite way of making uncountably many decisions? Any suggestions? Well, we're gonna use Zorn's lemma. Yeah. So the proof is apply Zorn's lemma. I guess I find it funny the way, like, the way this is often communicated as, like, I don't know, that, like, Zorn's lemma is this gadget that's going to give me, like, this set in some way. But I think it's really just sort of saying, like, we might as well just have the ultrafilter lemma be like an axiom, and, like, on its own merit we just sort of say, like, oh, of course you can just sort of make the decisions sensibly, like, I don't know, just like just make infinitely many decisions. It's sort of the same. I guess we're kind of reducing this case of wondering whether ultrafilters, non-principal ultrafilters, exist to we've already decided in, like, anything that fits Zorn's lemma, we've, like, asserted it to exist. So I don't know. We should leave that commentary to the side for the moment, actually. Okay, so what do we apply Zorn's lemma to? The poset. Yeah. Yeah, exactly. To the poset of filters on the whole set X, which contain F. And so the two steps of this argument are going to be, first, justifying why we satisfy the premises of Zorn's lemma, which is that if you have a chain of, if you have an ascending chain in this poset, any ascending chain, that such a chain is upper bounded by some such element of the poset. And then from there, like out of Zorn's lemma pops this maximal filter, and then I have to argue that a maximal filter is an ultrafilter. So I could just you can make the observation that, all right, given a chain of filters, maybe I'll just write down what that looks like, just so you have a better picture in your head. Chain of filters starting with F, which I'm also going to call F0, which is a subset of F1, which is a subset of F2, and so on. So the chain might be countably infinite, or okay. And so you can see that the partial order on this poset is the subset relation. So it's a matter of every filter in this chain might be adding more sets that it considers large. Okay, and so of course all of these are upper bounded by the power set of X, but this is not an element of the poset. The whole power set is not a filter itself. So that's just making that observation isn't enough for Zorn's lemma. You need to when you say every ascending chain is upper bounded, it needs to be upper bounded by something in the poset. So we need to identify some filter which is actually in the poset that upper bounds this chain. And in this case, we can just take the union. So their union is a filter. And so let me justify why. Well, firstly, axioms 1 to 3 hold for any union of filters. So I hope you see that this is also not controversial. So the first two axioms, or that the whole set is in the filter and the empty set is not in the filter. If you just take a union of a bunch of filters on X, you're not ever adding the empty set nor removing the whole set. So trivially, that's fine. And also in the case of needing every superset of a set in the filter to be large, you're also not removing any of the supersets of the sets that you start with from any of the filters that you're unioning. So all there is to check is really the intersection part. So now I'll argue that the union over this is the filter that this is the filter which is the upper bound filter for this chain. So this thing is closed under intersection. Because, well, if you take any pair of subsets in this big union filter, well, they come from two of these filters. Or like they might be from the same filter, but say for example, A comes from F0 and B comes from F1. Well, the only observation you have to make is that because there's a subset relation going on here up the chain, A, in this case, because A was in a filter that comes before B, we know that A is also going to be in the same filter that B is in because of that subset relation between the filters. And then because that particular filter is a filter, the intersection is also in that filter. So therefore it's in the union. So I'll write that argument now. because for any pair A, B in the union, where, let's say, A is in Fj, B is in Fk, and without loss of generality, let's just say that J is less than or equal to K. Because if it's not, then just switch I, and J. We have A is in Fj, which is a subset of Fk, because Fk appears later or at the same position as Fj, so it's a subset. So that means A is in Fk, so therefore the intersection what am I saying here? So A intersection B is in Fk, which is contained in the union. So the intersection is also in the union. Okay, so that shows that take any chain of filters, take the union of those filters, that whole set of subsets is itself a filter, and clearly that's an upper bound for all of the filters in the chain. So we've done half of our work now. So by Zorn's lemma, let me spell correctly. There is a maximal such filter by inclusion. So when I say maximal such filter, I'm talking about amongst the post set of filters on X containing F. Okay, so now I just have to argue that what I've got is this maximal filter is actually an ultrafilter. Proof. So we'll do this by sort of proving the contrapositive. So if I have something which is not an ultrafilter, then I'm going to show that it can't therefore be maximal. So say you've got some filter, and I'm going to call it F bar because it's going to be, I don't know, F bar is just the name I'm going to use for the maximal filter, but this just holds for any filter. So if a filter F bar is not an ultrafilter, then by not satisfying axiom 5, you have there's some set which the filter F hasn't decided on. So you have A is not in the filter, and X without A is also not in the filter. And so the claim is obviously that what we're going to do is just make this filter bigger and then claim that, or we claim that we can make the filter bigger first by adding, well, we could add either of these sets really. So let's add in the set A. So we're going to call A large now. And so the observation is that it has the finite intersection property. And so how do you see that? Firstly, when we're talking about finite intersections of sets in this set of subsets, we don't really care about the ones which don't involve A, because we already know they're not going to give us the empty set. Maybe I should repeat. The finite intersection property states that any finite intersection of sets from your set of sets doesn't yield the empty set. And so because F bar itself is a filter, if you've got some finite intersection that doesn't involve A, then we already know that it's not empty. So we just need to check that if you've got a finite intersection that does involve A, then it's still can't be empty. And so let's consider any finite intersection involving A can be written like this. It's like A intersection and then the intersection of a whole bunch of sets BI from 1 to some number n, with all of the BI in the filter F bar. And so if I just draw a picture, we're showing that we can't have this intersection be empty. So here's the whole set X. Here's A. If the intersection is empty, then they're sort of mutually exclusive. There's the intersection of the BIs. But then if it's empty, we'll then just observe that that the intersection of the BIs then belong to the complement of A. Oops. Let me draw this part first. So this is the complement of A. All of that space is X minus A. So then we have the intersection of the BIs is a subset of X without A. But then observe by, I think it was the fourth axiom, by number 4, the finite intersection axiom, we have BI, the intersection of the BIs is in the filter F bar. And so by the superset axiom, we should have X minus A should be in the filter F bar. Let me just rewrite this. And by 3, that should also be an F bar because it's a superset of this large set. But that can't be the case because we just posited that that X without A wasn't in the filter. This should have said F bar, not F. There's no F involved here. And so that produces a contradiction, so that you cannot have we're not finished here. What I've done is I've started with a filter which is not an ultrafilter. Then I've shown that if you have some set A which is not in the filter and its complement is also not in the filter, then what did I prove here? I proved that this set here has the finite intersection property. And so what can I use that for? It means that hence F bar union A generates a filter. That was what I proved earlier, that as long as you've got a set of subsets that of which you cannot create the empty set by taking finite intersections, then you can close it under intersections and then close it under supersets, and then you've got a filter. So F bar union the set containing A generates a filter properly containing F bar. So that means F bar is not maximal. So what I proved was that if you've got a filter which is not an ultrafilter, then it can't be maximal. And so therefore, if you have a maximal filter, it has to be an ultrafilter. And so therefore, the filter, the maximal filter that Zorn's lemma gave us, is therefore an ultrafilter. So that completes the sort of technical part, well, the work we did today. I guess I want to just say finally that I guess you might be wondering, okay, under no conditions, I've shown that you can use Zorn's lemma, but I don't know, you could use Zorn's lemma to, I don't know, prove that every vector space has a basis, but we do know how to, we can just start with a basis in mind, and we don't have to like use the axiom of choice or anything. But to my knowledge, in this case, like this is really the only method for like to create an ultrafilter under these conditions. Like I can't actually pick out just an example, even if I know that the set X is the set of natural numbers or something. And so this should feel a bit disappointing if like given my slogan at the start that I'm going to produce a concrete non-standard model using ultra products which depend on ultra filters, because there's this sort of gap in creating an ultra filter, or at least a non-principal one, which kind of critically just involves like knowing of the existence of such things, but like not actually being able to concretely describe an example.
So what is the input term that you'll put into this lemma when you're constructing these non-standard models, which is sort of the only information present then, if the rest is just a wrapper that says do Zorn's lemma or let Zorn's lemma give you something?
Sorry, could you explain that again? What do you mean?
Yeah, I can't ask a precise question because I don't know how you're going to use this. I'm just curious, in the cases where you're going to apply this to get an ultrafilter and then use that to construct a non-standard model of something or other, is it going to be the case that the filter we start with is somehow concretely described, and then we say take an ultrafilter which contains it? Or is it even less direct than that, where the filter...
because we start with at least n, we kind of know... all right, let me just say, the ultrafilter, its role is informing the... it informs the equivalence relation on the objects. That's the role in sort of like what the underlying set of the model is. It also then plays a role in the truth condition for the relations and also the term forming. But yeah, that's where it sneaks in. But I mean, to my mind, if you're happy to use Zorn's lemma everywhere else in mathematics, you should be happy to use it here. Any other questions?
None for me. I think that's good. I'm excited for part 2.
Cool. I also wanted to say so in the sort of first reference in the notes I distributed, there's a fair few interesting applications of filters. So for example, I don't know if you've ever heard of like some condition anywhere in mathematics that says something like all but finitely many points, blah blah blah. Then you can use filters to kind of generalize that idea. So you can describe convergence of a sequence with the Co-Finite filter. I think it's something like a sequence converges to a given limit point if all the open sets, the preimages of the open sets containing that limit point are all co-finite, as in there's only finitely many points that don't live within that set, is the idea of convergence. But when you then sort of if you then redefine convergence but with respect to a filter, you can use other filters and then say things like you can have like a sequence of like an alternating sequence like 0 1 0 1 0 1, and with respect to a filter that says that all the even numbers are large, you can say that sequence converges to 1. There are other ways. You can also there are other things you can do with it. It sort of has applications in topology. I think you can also prove Tikhonov's theorem, which I always found mind-blowing from metric and Hilbert spaces. Yeah, and of course you can use it to create non-standard models, which is what we'll do next week. But that's it for me. Thanks. Oh yeah, do you like the sparkles I added?
Yeah. Now everybody can find it there. Okay, thanks.
I thought you didn't like the secrecy, but I guess now that you know where it is,
that's right. Yeah, now I know I like it. Yeah.
I was thinking of making some kind of like teleport system where like you walk into one tree and like pop out of another one. Because basically as a solution to like at the moment I've kind of just been shifting the spawn location so that you end up where we're going to be doing the seminar, but I don't think that's I'm not going to be able to do that when we have multiple pockets and like different things are happening in different pockets. I don't know. Oh, you can't get me?
I don't know. Not very easily.
Yeah, so the point I was making before is that whenever I like applied Zorn's lemma or something, I don't feel like I've like I could kind of be equally satisfied if I just sort of like added like an ultrafilter axiom.
Sure. Yeah, I agree.
Like there's not sort of like much going on. I'm just sort of classifying it as this tucks in the same set of examples that like Zorn's lemma was introduced because of like specific instances like this, right? Where we wanted to like get some maximal element of some ascending chain. And so it's just sort of a classification of all those situations into like one particular lemma that posits the existence of the maximal thing in all those cases.
Wasn't perhaps paying close enough attention, but so you prove that every maximal filter is an ultrafilter. Is every ultrafilter maximal?
Yeah, yeah. I think that one is kind of simple.
Mhm.
Um,
Okay, well,
like
that's a natural condition.
yeah, if you can make it any bigger, that just involves adding one of the co-large sets. But
Hmm.
the large set is already there, so that if you take the intersection of
Right,
that, you'll
right.
get the empty set.
Hmm. Yeah, makes sense. Yeah, given my background, I don't object to using Zorn's lemma. Um, I guess what I feel a little more wary of it in this context because I'm often, I suppose, invited to think of I guess in some circumstances you're invited to think of constructions as being more accessible than they really are in some sense, right? So like if deep down somewhere there's hidden an application of Zorn's lemma, but you get the impression that someone higher up the chain is trying to con you into thinking that actually you have some handle on this object and it's not just
Mm.
some
Yeah, because we
like
don't
deep
even
down in there
have
there's like use magic wand.
yeah, like there's no sort of thing that we can use to sort of uh, access like the maximal filter. It's just it's just the kind of belief that it's there.
Yeah, which is fun.
Like I guess the only in terms of like existence, like a priori you might think, all right, you can satisfy the first four axioms, so just the filter axioms, but then maybe like uh, in some way trying to add the fifth axiom like create some internal inconsistency that like because it's not just making infinitely many arbitrary choices. Like at the end of it you have to sort of still satisfy the original axioms, um, and so you might worry that like something goes wrong in getting there.
Mm-hmm.
But I guess because I proved it, I don't know, I in applying Zorn's lemma, I guess you kind of uh, you reduce it to just the task of making a bunch of arbitrary choices.
Mm-hmm.
Um, yeah, I'm kind of interested why you have a sort of double, uh, I guess, standard for using like axiom of choice and Zorn's lemma like in sort of standard mathematics, and then like in this context, like you're wary of it. Like what's the what
Oh,
informs that?
I think uh, I think people are just scandalously careless about mixing mathematics and meta mathematics and being clear about when they're doing it. And therefore, I want to raise up a red flag when it comes to reasoning. I mean, I don't think
Right.
I'm not saying you're doing it, but I'm saying that clearly people do it, right? And therefore, my protest is to whinge every time somebody, you know, um,
Well, I mean, I think it's odd because I don't think it's the case that like okay, maybe there are people that are careless and just not thinking about it, but I think it's a pretty like uh it's kind of a off like a commonly held view that like mathematics is mathematics, like and sort of intentionally having that perspective. Um, like I mean, you might sort of believe there is a difference, and like you can't. I don't know. Maybe certain things are illegal to do in meta mathematics, but I kind of find it weird because like that just leaves meta mathematics as like as the realm of like philosophy or something, and as a
No,
mathematician
no.
it's like, what, I'm not allowed to use my tools to like understand this?
No, I wouldn't put it that way. I would say that, okay, you could. I would say the default mathematical philosophical orientation is to view mathematical objects as having some sort of Platonic existence, and then the symbols we write down and the proofs we, that logic is sort of about reasoning correctly about those externally existing objects. And we sort of believe in them independent of any particular formalization or foundations. And that, I would say, is pretty clear from the way we orient ourselves towards foundations and their paradoxes, and the way we think about, ZFC as being one foundation. But we don't really believe that if we were to switch to NBG or Topos theory or whatever, that like the true nature of the circle would change. We think we might be able to prove different statements, or there might be a different flavor, but we're not convinced, at least absent very strong evidence, that it's really different. So that seems to me to indicate a pretty strong a priori belief in something like the independent existence of mathematical objects, at least a certain kind of mathematical object, but what kind? So, okay, if you take that as a given, then the question becomes, well, how good is that logical structure, that symbolic structure that we use to reach out and try and touch that Platonic realm? And that's, what I think of as what people like Gödel were trying to do. But then you see, you can't really, if that's how you think about what's going on, that you've got the Platonic realm you can't access, and then you've got this puny symbolic stuff that you get to do on paper, and you're asking the question, well, how powerful, how much can I trust this stuff? Then you don't get necessarily to naively think about it in the Platonic way, because you're very much engaged exactly in the question of what is the gap between the symbolic stuff and the Platonic transcendent stuff. So to engage in the exercise in a spirit of, well, my symbolic stuff is really just the Platonic transcendent stuff is sort of to miss the point, or to beg the question in a way. You see what I'm saying?
Right. I definitely don't think the same thing. I guess that what's interesting to me is whether you whether the journey of foundations is, like you were talking about, the Platonic realm and then the sort of symbol realm, whether you start with the symbol realm and try and get to the Platonic realm, or whether you're starting with the Platonic realm and like sort of attaching that to symbols. I mean, I feel like it's a settled question that we've like gone over many times, that if you can't start with the symbol realm and then like achieve the Platonic realm, because various things get in the way, like Gödel's incompleteness theorem. And so I think I'm more of the mind of like I like to think of like, so somehow we're like internally opinionated on this Platonic realm, and we have some sort of internal notion of truth that we can sort of say this set is not equal to that set, or that it contains this, or like we have some sort of
Gödel called it a sense, very much like our senses of the physical world. He strongly believes that we have a sense of that.
Yeah, so I guess I'm sort of, therefore then, all right, can we start there, and amongst those sort of that sense, and I don't know, the sort of mathematical sense in that, you can you make like a small part of that is like the primitive tools that you need to make like your sort of logical system with all your symbols, then you then reason about that logical system, come to conclusions, and then sort of reflect on what that means about like the Platonic realm.
Mm-hmm. Yeah, I'm fine with that. That's how I would more or less think about it. I suppose, however, that it's possible to be unsophisticated about that and to I mean, that's a fairly complicated proposition that you just laid out, right? It's quite subtle. And I think that sometimes foundational discussions are used to try and convince people of a much more simplistic take, which is sort of in some conceptual fashion exactly what we know isn't true, right? That we just erect this simple, finitistic, symbolic structure, and it is an unerring guide to what is and is not the case about the Platonic realm. Whereas what you're very much in a modern sense giving up on that project almost completely, right? So you're sort of taking the attitude of a mathematician to logic. You seem to be a mathematical logician, and saying, okay, well, let me study logic and foundations very much in the spirit of a mathematician and not worry too much about trying to pick myself up by my bootstraps from zeros and ones laying on the table that I push around with a fork and get all the way to heaven. You're not seemingly very motivated by that project, but many people interested in foundations deeply, deeply are interested in that project.
I just like worry that it like I guess the discussions it sort of leads to, in my experience, are more like they just start to like they inherently become more vague, and then they like I don't know. I just feel like you end up achieving less, or I don't know. You're just talking about you're just philosophizing.
Right, but maybe you should admit that the kind of questions you might be interested in are nonetheless still motivated by some aspect of that quest, right? So to be interested in foundations, I mean, if you don't view that, if you're not interested in that project in any way whatsoever, then why be interested in foundations? Are you just kind of like, oh, look, there's set theory. It's about as good as geometry. It just has a different flavor. Oh, neat.
So,
is that it?
So let me restate it as like I guess I don't mean to say I'm not interested in that discussion. I just find it unproductive to zoom out, as in like try and go towards the like figure out what the meta theory is, like I don't know, start with ZFC and trying to figure out like what's the meta theory of ZFC and then what's the meta theory of that thing. I think it's like I get what I'm gonna talk about tomorrow is like this whole idea of like I'm kind of saying, all right, bring your own foundations to the table. Like somehow you're able to like talk about mathematical things in a way that makes sense in your own head, and if you want like but then hopefully you've got enough to talk about ZFC.
But then, so what you're bringing to the table is in particular a presumption that ZFC is consistent then. If that is, if your meta theory has ZFC in it, then do you just come to the table prepared to believe everything is true? No. So therefore you're at least, you're presuming consistency of ZFC. That's a fair thing to bring to the table. That seems like a lot to drag to the table.
Yeah, okay, well, let me just complete the story of So okay, say you've brought that to the table. Uh, Within that, we can reason about a formal system, and then we can come to some interesting conclusion about, all right, this formal system can't tell the difference between this model and that model, which is clearly not like the model you had in mind. And like, of course, it rests on the sort of prior consistency you brought to the table. But I mean,
it still seems to say something real, nonetheless.
yeah, like I think, like, I guess my idea is, instead of zooming out, you like zoom in for a bit, like discover some consequences, and then try and like lift that to the meta theory discussion in some way.
Okay, would you agree with the following proposition then? So just as, say, as a geometer, I might prove something about some algebraic variety, and then I'm aware that I'm using ZFC, and if ZFC turns out to be inconsistent, then in principle my proof may be invalid in whatever future foundations we shift to avoid that particular problem. But I don't believe that. I'm pretty sure that some version of that will remain true, and therefore I feel invested in its reality in some way that's beyond the foundations. I can't say what that means, but I'm sort of convinced to some degree of that. And in a similar way, you feel some truths about sets or models or logic, even though you're engaged in the exercise with a presumption of consistency of ZFC, perhaps, that those truths are somehow beyond those particular foundations. But then you have to worry, like, I mean, the proofs that seem pretty close to the axioms of ZFC then seem a bit riskier in that sense, right? Like, surely you can't be as convinced of the independence of the foundations. You're not as convinced of the truth of some proposition about the 10 sphere as you are about some proposition about sets, right? Don't you feel that there's something a bit more dangerous about buying into the transcendent truth of sort of model theoretic statements as versus geometric statements?
Well, on that last point, I think, I don't know, like, this is, I view model theory, and I think the like model theorists talk about model theory taking place within the, like, in largely the same way as like algebraic geometry takes place in like some foundations. Like, I didn't like,
well, I'm just
I don't see it being discussed as like we're talking about meta-mathematical objects.
Oh, I don't care how people talk about it. Just because they feel comfortable with it doesn't mean they should feel comfortable. I mean, I think I'm expressing a pretty commonly held feeling that when people look at set theory, say, in a discussion of very large cardinals, there's a feeling that maybe that's not real. Maybe that's some artifact of our current foundations that won't survive its collapse in 56 years or whatever. I mean, I don't think maybe people talk about it very often, but that's kind of one of the reasons why people were skeptical of set theory for a long time, even though they might agree that the proofs don't have problems with them. There's still a lingering sense that they're not real, whatever that means. But anyway, yeah, I take your point. Yeah, just I mean, it sounds like I'm defending the reality of geometry against the inferior subjects of model theory or set theory or something. Well, that's not really true, because if you look closely, there are many things in geometry that, if you or homotopy theory or whatever that have it's not like you can separate these subjects, right? Or this your intuition about what is and is not natural is constantly being refuted by experience when you get to know, various ways you can embed set theoretic issues into natural geometric questions or topological questions. So yeah, you have to. The project of figuring out what is and is not sort of likely to survive a shift from any given foundations to another is it's not at all obvious.
It's because it's difficult to compare them because it's not like they're the same sort of background ideas but with different axioms. Like I guess that's
right.
the same. That's the case with ZFC and NBG. But when you switch to something like type theory, like I think it's if you're not used to both of them, I don't know how you can. It's like probably hard to make the comparison because they say they're saying different kinds of things, not just disagreeing in some simple way.
All right, shall we leave it at that? Thanks, Billy. That was interesting.
Cool. We'll see you next week.
Good night.
Hope I can fit it in one lecture, but maybe I'll spill over to another seminar.
See you around.
Yeah.